Hello, my name is Garrett Hinton, and this is Physics Lab 5, Slinky Drop for the Choose Your Own Adventure Physics Lab. To get started, here's a table of contents. I'm going to run through an introduction, then go into assumptions, um, and then my tracker, glow script computations, and then results and conclusions. To start off with, the purpose of this lab is to measure and predict the motion of a stretched out Slinky being dropped from rest from a certain height that was being held up. And then here's a short preview of the results, um, comparing the observed fall versus the predicted fall. And then to start with the assumptions and the principles, the system is the spring or the Slinky, and the forces acting on it by it. Um, and then the surroundings are the earth and air, as there is a drag force affecting it as well. Okay, to start, we have Newton's second law, Vf equals V initial plus F net over m times delta t, and then F net equals the force of gravity plus drag force plus the force of the Slinky itself, and then gravitational force equals W, which would be weight. That would equal negative mg times j hat. J hat would be the direction that the Slinky is falling, which would be just um, downwards, basically, in the y direction. Um, G is Earth's gravitational force, 9.8 newtons per kilogram, or meters per second squared. As for drag force, that would be air resistance. So the force of drag is proportional to negative magnitude of velocity squared times v hat. And then the magnitude of v is the object speed. And then there's the velocity direction. So here's the tracker with the initial conditions, mass of 0.25 kilograms, initial position at that point right there, based off the proportion of Mr. Veritasium's height that I found on Twitter, and then delta t, the entire falling of the object took about 1.48 seconds. Here's the script. These are the initial conditions as described before, with the initial position and so forth, as well as the drag coefficient down here that was found and described previously in the previous slides. Here is the script starting at 0.377 seconds that actually shows the falling of the Slinky. Because what happens in the video is as the top of the Slinky is released, the bottom does not fall until the top catches up with it. So that happens at 0.377 seconds, and then the entire system falls to the ground and is then acted upon by drag force. And this is for the entire system, um, as it is all falling, um, and how it plots out, but using the principles um, explained in previous slides, these were plugged into the glow script to make the computation actually function. And then here are my results. The dark blue is the observed, whereas the light blue is the predicted. There is a little bit of this discrepancy in here, particularly at the end, because um, the Slinky hit the ground, whereas the model, I think, was assuming that it would continue on downwards. And I also believe the model factor in a bigger proportion of drag, whereas the predicted probably with some discrepancies in the tracking on the tracker. It could have been a little bit more accurate. Plus, I'm not entirely sure if it had a proper chance to incorporate drag. There's also certain tensions and forces acting upon the slinky as it fell. To do a better comparison, I would have to model or track the top and bottom of the slinky and compare them and model them. Thanks. That's it.